All right, so this is going to be a video all about limits. It's usually the first unit that's covered in any AP Calculus AB course or any college level Calc 1 course. Sometimes you do see limits though in classes like pre-calculus as well. Either way, this video is going to be very all-encompassing of the entire idea of limits. And this first section is basically just going to be going over the idea and the concept of limits without really looking at any problems, just kind of getting you an idea, getting your feet wet on what limits are all about before we start solving problems with them. What I have on this screen right here is essentially a bunch of slides, a bunch of images that I'm going to use to explain the concept, and you're going to notice that I use this in other videos as well. So hopefully it paints hopefully it paints a better image as to what we're covering. I am going to keep these videos semi-informal as a way of kind of explaining the concepts in a more straightforward manner so it makes sense to you. So that's what you're going to see on these slides right here is a bunch of pictures, images that we're going to use to explain the idea of limits. But before we get into the backbone, the main part of calculus, which is limits, I'm going to start with this first slide right here. It says the map of mathematics, and you'll notice that it's very, very vast, and this is not all encompassing by any means. I found this image online, and I just think it's great to show basically like what it says, the map of mathematics. It's very, very vast. A lot of the stuff that you have covered in previous math classes is usually looked upon right here, so you should start recognizing some of these words here. For example, it says algebra right here. So we have some algebra, mathematical notation, zero, when that first came about, counting, negative numbers, that sort of thing. And it's got, it starts with these origins here, so I kind of like to start there. And then it kind of builds from this. And in a way, math is all basically just fancy ways of counting certain things. And then it could just be extrapolated to so much more vast things, as you can see on this map right here. What we're going to be focusing on, or actually what I should be saying is you've also covered other things here as well before I go on to the new stuff. So natural numbers is just regular old counting. Rational numbers is just a ratio of two numbers. Complex numbers, if you remember I, you'll notice this imaginary number unit here, I. You've probably seen some exponential stuff in pre-calc or algebra 2. We got pi here, we got prime numbers. We're going to be dealing with more stuff with infinity in this course. Real numbers, integers. It says right there arithmetic right here with the add, subtract, multiply, and divide. You kind of get the idea. You might have done some stuff with probability. Maybe you've taken a stats class before. A lot of this other stuff though, I guess geometry is right here. Some trig, there's Pythagorean theorem right there. But as you can guess, we're going to primarily be focused on this little section right here, calculus. And we're pretty much going to actually be solving pretty much everything that's in this little image right here. We're going to be dealing with the concepts that are in this image. So it says calculus. If you notice, it comes from this changes thing because that's what calculus is all about. It's actually the mathematics of change, just infinitesimally small change. In essence, is what we're going to be looking at. We have these differentials, which we're going to talk about in more detail. This is the derivative here, which is a main focal point of calculus. Integral is the other main focal point. And you could do it to solve certain things, which we're going to go over in a little bit more detail. But just kind of like to show this graphic because it shows the vastness of math, and we're just going to be focusing on this major section right here. But there's a lot more other stuff that, if you're really into mathematics, I highly recommend looking into this other stuff as well. Even if it's just, on a surface level, it's still super interesting stuff. But we're going to go pretty deep dive into this calculus section right here throughout this course. The main ideas of calculus, so I made my own slide right here, that it shows the two main ideas of calculus, namely the slope of a point and the area of a plane. So slope of a point and area of any plane. The main thing you need to know for this slide right here is that limits are what makes it possible for you to find these two things. So these two things, slope of a point. So you have this one point right here, and you're making a tangent line here where it just kind of grazes that one point. And then we're basically trying to find the slope of that line, which is basically the slope of that point right there. You can't actually do this using algebra. So old school algebra, when you found slope, it was, change in y over change in x. You had two y values, you had two x values. You would subtract those and find the quotient between those. So subtract the y's divided by subtracting the x's. Well, this time there's only one value here. So it's almost like an impossible value to find using algebra. But with limits, you actually can find this value. Okay. The other part, the main idea of calculus is the area of any shape. So if you notice, this is just a kind of a weird shape. Kind of looks like a trapezoid, I guess, if you want to look at it that way. But it's not just some basic shape that you've seen in geometry where you can find the area of it. Well, limits also help you find that value as well. We're not going to focus on that so much in the beginning. That's going to be more of the second half of the course. But for the first part, I kind of want you to frame your mind on finding the slope of a point, and you actually need limits to figure that out. We haven't gone over limits yet, but we will, and hopefully it makes more sense as we go. I'm just trying to, plant the seeds to your understanding a little bit for this first part of the video. Okay, so this next slide right here just says slope of a point. Again, to find regular old slope, we would subtract two y values and divide that by the difference of two x values. Well, here we only have one. So if you use just that one coordinate, that means that this value and this value would be the same, as well as this value and this value being the same. So if those two are the same, you would end up with a 0 over 0, which is indeterminate form, and it's undefined using algebra. But that's what's great about limits. If you use limits, you can actually find this value. And again, that's what we're going to be going over a little bit later in the course. Okay, this next slide just shows area of a plane again. I'm going to kind of skip that for now. So yeah, unit 1 is all about limits. Limits let us find impossible values, and that's basically what this slide is showing. If you were actually going the speed of light or approaching the speed of light, what would happen? Why is it impossible according to math? Why you can't actually do that? We're going to talk about this equation a little bit more detail throughout the course. It's one of Einstein's equations actually, that show that if this v right here gets closer and closer to c, you end up with a specific value. Essentially, this is becoming infinite mass. But again, we're going to talk about that in more detail later. This next slide, it says map of calculus. So I showed you that other slide that said map of mathematics. This is just the map of calculus. And basically, it's meant to just show you that if you look at all of the math that you took before this course, so you learned algebra, you learned geometry, you learned some trig, you learned some series. If you mix it with limits is basically the bridge from all the math that you've learned before into this calculus. And we're going to be learning that first main idea, that slope of a point. The main point of calculus, that first point, the slope of a point, that is called differentiation. We're going to go over that in more detail in that second unit. And then the second half of the class is all about integration, which is the opposite of differentiation. And then in Calc 2, you're going to be going over this infinite series. But the main thing that I want you to see on this slide is just that limits are needed to bridge the math that you know to the math that we're going to be learning in this class. Okay, so again, you don't really have an idea. So you really don't have an idea of what limits are. Just know that they're super important, and it helps you find certain values that are normally impossible with algebra. Here's a breakdown of the entire unit. We're going to go in more detail later on in this video. It's going to detail each one of those sections, and so you have a firmer understanding of what limits are all about. But the main thing that I want you to get on this first part is right here. It says moral of the story is that limits allow for the solving of algebraically impossible values. So using algebra, you can't necessarily find these values, but with limits, you can find those values. And that's the main thing that we're going to be going over. And then this last slide right here is basically a breakdown of everything that we're going to be covering in the unit. By the end of this unit, you should be able to explain every little part of this image. So the next part is we're going to go into a deeper dive of this unit and start with that first section. All right, so the first subsection that we're going to be going over right here, 1.1.1, is all about defining and estimating limits. This is from section 1.1, which is just basically about finding limits, evaluating limits, that sort of thing. This first subsection, though, is just defining what limits are, so you have an understanding of them. The previous part of the video didn't really explain exactly what limits are, just showed the importance of them and why they're needed for calculus, namely to find the slope of a point and to find the area of any shape. So what we're going to be doing, though, in this section right here is just figuring out exactly what limits are in more detail, as well as estimating them, namely with tables and graphs. So let's go through this here. This first section right here just talks about what's called limit notation. So we have this new notation here where it says LIM. What this translates to is take the limit. Okay, so this right here, if it was translating from math to English, it means take the limit. So that's where you start. Take the limit of f of x. So essentially what it's saying is find the value that this y value, so f of x just means y, so if you remember y is just a fancy way of writing f of x a lot of times. So this is basically saying what is the limit of y, so what is y getting closer and closer to as x, so now we're down here now, as x approaches, this means approaches, so I'm going to write that in real quick, as x approaches some other value. So basically the answer would be this L part right here. So probably doesn't really make a lot of sense there, so let's kind of rehash some of these parts. Essentially what you're doing is your x value is getting closer and closer to some value. Let's just say it's c. As x gets closer to some value c, and c can be any value. It could be 1, 2, 3, a million, 2, -2, whatever, it doesn't really matter. As x approaches some value, where is y approaching? Okay, the answer to this question right here is this L. Okay, x is getting infinitesimally closer to some value, so let's just say it's getting closer to 1. So you can think of it getting closer to 1 with 0.999 repeating. Okay, that's getting closer to 1, but it's not actually equal to 1. And that's an important thing to address with limits, is that it says x is approaching c. Okay, it doesn't mean x is equal to c. In fact, it's not equal to c. It's just getting infinitesimally closer to it. So if I had an example where, let's just write it up here, where I had something where it's like x is approaching 1. Okay, that means x is not actually equal to 1, but it could be equal to 0.999 repeating. Okay, so you can just kind of imagine 0.9 repeating, or you can imagine 1.0000 repeating with a 1 at the end of it. Okay, both of these values are approaching 1, but they're not actually equal to 1. So you're just getting infinitesimally closer to 1. That's essentially what this x arrow c means. It just means approaches. So when you see a limit problem, what it's basically saying is x is going closer to some value. Where's the y going? What value is that getting closer to, if anything at all? Okay, so that's basically just an intro to that notation. It's going to make more sense when we actually do examples, but you want to make sure that you can translate all of that math into English so you have a better grasp and understanding of this calculus stuff. Okay, this next one is a limits GIF. I am just going to not go over this right now because it's not actually animated, it's not moving right now, so we're just going to ignore that. The next thing right here is limit notation. Okay, it's basically what I just said, only it's actually written out in English. Okay, so we have right here the limit as x approaches c of f of x is equal to r. Okay, before it said equal to L, sometimes it's equal to r. It doesn't actually matter, but the same premise holds true. The LIM translates to take the limit of. Okay, so that's what the LIM means. We're translating that math notation into English. Take the limit. The f of x translates to f of x, just standard what you've seen in previous algebra classes. The x arrow c, that's x is approaching c. Okay, you have to understand that x is actually not equal to c, but it's just getting infinitesimally closer, and it's getting infinitesimally closer on both sides. So if you want to take the example that we used before, x is getting closer to 1, that means 0.9 repeating. It also means 1.00001. Okay, and then it says right here, r represents any real number. So we're not going to deal with complex numbers with this if the limit actually exists. We are going to be talking about what happens when the limit does not exist. That's a whole other ballgame. Okay, those are called non-existent limits. It's actually the next section we have right here, non-existent limits. There are instances in which the limit does not exist. If you've ever seen Mean Girls, you'll remember at the very end, Lindsay Lohan says the limit does not exist. She was actually doing calculus with that problem, and the reason why the limit was not existing in the movie is because the limit does not agree on both sides. But we're going to talk about that in a little bit more detail later. But the main thing is x is approaching a value c, y is going to be approaching some other value. In this case, it's r. That is the answer, whatever that r value is. Okay. If r doesn't have a value, then the limit does not exist. Okay. Limit notation. Okay, here's an example with a graph. Okay. If you notice right here with this graph, it's a hole. Okay. So that means f of 2 is undefined. Okay. The reason for that is because there's no value there. It's an open hole. But if you notice, if you approach the x value on both sides, so we're approaching on this side, we're approaching on this side, there is a y value that it gets closer to because it's approaching on both sides. So f of 2 is undefined, but the limit of f of x as x approaches 2 is actually equal to 4 in this case. Okay, as x gets closer to 2 on both sides, so the 1.99 repeating and the 2.01, I'm going to write that in here. This is 1.999 repeating on this side, and this is 2.00001 repeating, or 2.0 repeating with the 1 at the end of it. Wherever this is approaching right there, it's the y value. In this case, it's 4. Okay, that's essentially our first limit problem based on this limit notation that we're looking at. And this time we used a graph to solve it. Okay, graphs come in different flavors, so you could have a graph that looks something like this. And what we're going to do in this case is we're actually going to try to find some of these limits. So f of x is defined as that graph. Let's say that we're trying to figure out the limit as x approaches 0 of f of x. Okay, that means x is getting closer to 0 on both sides, so that means it's approaching 0 here, and it's approaching 0 here, because x equals 0 is right there. You approach on both sides, you'll notice it meets in the middle, right here, at 0. So the answer for this first problem right here would just be 0, because the x is approaching on both sides. I use little arrows to kind of show you, and the y value is 0. Okay. Let's do another one where we're doing the limit as x approaches, I don't know, let's approach 1 of f of x. Okay. If you notice right here, here is x equals 1. Here it is on the graph. We're approaching from one side, and we're approaching from the other. They do meet in the middle, and that y value where they meet in the middle is 3. So the answer for this one would be 3. The limit as x approaches 1 of f of x, or you can say the limit of f of x as x approaches 1 is equal to 3, because the y value is getting closer and closer to 3 as you get closer and closer to 1, as x gets closer to 1. All right, let's do one where it doesn't exist. Okay, let's do the limit as x approaches 3 of f of x. Okay, the limit of f of x as x approaches 3. Okay, if you notice, here's x equals 3 right here. If you notice it goes this way here and this way here, you're approaching on both sides, so 2.999 and 3.001, so above the 3 and just below the 3 on both of these. If you notice, they do not equal the same value. They're not meeting in the middle. Okay, the orange one met in the middle, the red one met in the middle, but this green one here, it doesn't actually meet in the middle. There's a jump there. So because of this, you would say that this limit does not exist, and you can just write DNE for this one. Okay, this is our first example of a non-existent limit. Okay, the limit does not match on both sides for the y value. The y value is 2 on one side, and then the other side it's negative 1, 2, 3, 4. Okay, 2 is not equal to negative 4, so the limit for that one does not exist. Okay. Let's keep going here. Let's do another one. Let's do the limit as x approaches negative 2 of f of x, or you can say the limit of f of x as x approaches negative 2. If you notice right here, here's x equals negative 2. On the graph, you're approaching one side, you're approaching the other, and if you notice, it meets in the middle right here. But you might go, wait, what about this thing right here? Okay, this is just an island. It's not really the correct terminology for it. I like to call it an island though. There is no sides to this. So for all intents and purposes, you can just ignore islands. You don't really need to worry about it when you're doing stuff with limits. Now, if you said something like, what is f of negative 2? Like if I wrote, what's f of negative 2? Then you can say it's negative 6. Because it goes down 1, 2, 3, 4, 5, 6. But in this case, x is equal to negative 2. The y value is negative 6. But this is the problem is asking right here, the limit of f of x as x approaches negative 2. So you would actually say it's equal to negative 2 because the y value right here, where they meet, is equal to negative 2. Okay, very fundamental understanding. You might think this is a little bit easy right now, and you might think, what's the big deal on this? Why do we need these limits? It's going to make more sense later on, but for now we're just finding limits graphically. It'll make more sense when how we can use this to figure out the slope of a point in the area of any shape. Let's keep going here. Okay, we got another problem right here. Finding limits graphically. Okay, this one right here, A, it says the limit of h of x as x approaches 0. Okay, this is defined as h of x over here. We're approaching 0. Okay, well here's x equals 0 right here. We're approaching from both sides. And the answer for this one should be negative 1 because the y value right here is negative 1. Okay, the next one, x approaches negative 1 for this limit. So the limit of h of x as x approaches 1, not negative 1, 1. Okay, well here's 1 right here. Here's the x value. It's approaching on one side. It's approaching on the other. It meets at that y value there, which in this case is going to be 0. Okay, the next one, x approaches negative 1 for this limit. So we have negative 1 right here. We're approaching it on this side, and we're approaching it on this side here. If you notice, there's a jump. On one side, it's 1. On the other side, it's negative 2. So because they don't agree, the answer for this one is DNE. And lastly, as x approaches 3 right here, here's 3. approaching here, you see a jump. You can't have a jump and find a limit. If it doesn't agree on both sides, it's going to be a DNE, does not exist. That's finding limits graphically. Okay, these two examples right here. We're going to do more of these as well to really cement this in. Hopefully this is making a little bit more sense as we go. You're figuring out the rules. Sometimes the hardest part of this is just the notation, because if you notice this notation, it is kind of weird from what we're used to. Okay, this kind of notation right here. It takes a little bit of getting used to with the LIMs and the X arrows, the X approaching. But hopefully that makes more sense as we do more and more examples. So that's graphically. The next one is numerically. So now we're using a table to figure out the values. And the thing I want you to understand with this is we're still getting infinitesimally closer on one side and the other, only this time we're using a table. In fact, I actually did this whole thing right here in the TI-84 calculator. So if you notice, I can't plug in 2 to f of x. And we don't know what f of x is. It just says y sub 1. So I'm going to write y sub 1 is equal to f of x. We don't know what the function is. It doesn't really matter. We can actually figure out the limit just by looking at these numbers here. So if you plug in 2, it's undefined. But if we use limits, we can figure out what the value could be by getting infinitesimally closer to that 2. So if you notice it's 1.9, then it's 1.99, 1.999, 1.999. If you notice, as you get closer and closer to 2, that's what these values are. They're approaching 2. These values are getting closer, the y values are getting closer to 4. So because of that, the limit as x approaches 2 for this one could be equal to 4. But you have to make sure that it matches on both sides. So that's what I'm going to do with the other side right here. 1.999 repeating is less than 2. Now we're going to do 2.0001, which is greater than 2. So if you notice this right here, it's getting closer to 2 still, but it's getting closer to 2 where it's bigger than 2. But if you notice, it doesn't change anything with the y. The y is still getting closer to 4, so the answer actually is 4 for this because it agrees on both sides. It agrees with the numbers that are bigger than 2 and agrees with the numbers that are smaller than 2, but are getting infinitesimally closer to 2 on both sides. Okay, so it's still using limits, only it's numerically rather than using a graph. We're going to do another one here where this time the table is more horizontal than vertical. And it says right here, x approaches 1 from the left. If you notice, it's getting infinitesimally closer to 1. When it's plugging in 1, though, it doesn't actually exist. On the other side, it's approaching 1 as well. It's just getting closer to it that way. And it's saying, what is this value? Now, it could be undefined here, but either way, the limit of f of x, in this case, f of x, as x approaches 1, would be 3. And you can kind of see it right here. It says f of x approaches 3 on both sides. If you notice, it's 2.313, 2.710, and then 2.997. That's close to 3. 3.813, 3.310, 3.003, getting closer to 3. So because of that, the answer for this would be 3. Okay, the limit of f of x as x approaches 1 is equal to 3. As x approaches some value, in this case 1, the y value is approaching 3. Okay, now we're going to get into more of the example problems that you would likely see on an assessment, a quiz, a test, that sort of thing. So definitely make sure you pay attention to these. In fact, what I would do right now is pause this, read through it, and then try to answer it, and then unpause it, and then watch as I go over it, and then you can kind of grade yourself and your understanding of where you're at so far with these problems. So I would pause it real quick here, and then unpause it once you have the answer, once you think you have the answer, and then we're going to go over it. All right, hopefully you paused it. It says let f be a function that is defined for all real numbers x of the following, which is the best interpretation of this. So it's basically saying, bro, translate this math to English. Okay, so we have to figure out A, B, C, or D, which one that math that's written right there, which one of them translates to English A, B, C, or D. Okay, the first one, it says the value of the function at x equals 2. Right there, that's the dead giveaway. It's not x equals 2. Limits always approach a certain value. So the x is approaching some value c. It's not necessarily equal to it for a limit. Limits are never equal to it. It's just infinitesimally approaching it. You have to understand that it's not equal, just infinitesimally getting closer. So in fact, anything with an equal sign, this one right here as well, cannot be the answer. It doesn't matter what the other numbers are. So now it's between c or d. This first part says as x approaches 2. This one says as x approaches 7. Well, x is approaching 2. You can see it right there at the bottom. It says x arrow 2. That means x approaches 2. That means it cannot be d, which means the answer is c. As x approaches 2, the value of f of x approaches 7. The values of f of x approach 7. So the answer is c. Hopefully you got that. We're going on to another example. And again, I would pause it here. And I'm going to try not to repeat myself too much about pausing it. Just know that you should probably pause it and see if you can actually get the answer for this on your own, and then unpause it and see if you got it right. So pause it here. Okay, and hopefully you got the answer. Let's go over it. It says right here, what is the limit of f of x as x approaches 2? So we're approaching 2 on both sides. Remember, with limits, we do not want to look at islands. Okay, we do not want to look at those isolated points because there's no sides to them. Okay, at this point right here, that just means x is equal to 2. We're not equaling 2 ever. We're approaching 2. These are not the same thing. Approaching 2 is not the same thing as equal to 2. Okay, approaching 2 means you're approaching it on both sides. That's the 1.9 repeating and the 2.0 repeating with the 1 at the end of it. That's not correct math notation, but you get the idea. We're going from the left and from the right, and we're approaching and we meet right here. In this case, it's meeting right at 2. So the answer for this one should be 2. Again, ignore the island. Do not get tricked up on that. Here's another example. If you want to pause this and then unpause it, we'll go over it. Of the following tables, which best reflects the values of g for this limit right here? So now we have the math notation, the limit notation, and we're saying, what does this look like if it was put into a table? Okay, well, x is approaching 9. So right away, what I'm going to do is look at the top part. That's where the x's are right here, and see which of them are approaching 9 from both sides. Okay, the first one is definitely not. It looks like it's approaching 5 from both sides. So it's definitely not A. The other ones, though, are approaching 9. You can kind of see in the middle, they all approach 9, which is kind of nice. Okay, but now we got to figure out which one are those are the answers based on the other value. It's definitely not A. So let's look at B. It's approaching 5 here. Here it's approaching 5 on one side and then 10 on the other, so that's definitely not it. This one, so you can see it's getting closer and closer and closer to 5, closer and closer and closer and closer to 5. This one's got 10 in it, so it's definitely not C. The other one is approaching something, it's like 100. This one's, I don't know, kind of approaching 5. I don't know. Either way, it's definitely not D. The answer for this one should be B. Let's go to example number 4. Again, pause it. Try to work this one out. And then unpause it, see if you're correct. This is a very conceptual problem. If f of c is undefined, does that prove or disprove the existence of a limit there? Okay, the answer for it is neither. Okay, because it really depends. And probably the best way to show this is just to draw an example. So I'm just going to graph a really simple example where it says f of c is undefined. So I'm just going to make up some point c as being like right here. And it's undefined, so I'm just going to make a little hole there. Okay, does that prove or disprove the existence of the limit? Well, it would prove it if the graph looked something like this. Okay, so if the graph looks something like this, you could see it's approaching on one side, it's approaching on the other. The limit does exist for that. But I could have easily redrawn this. So instead of having it there, I can make the tail end down here, like this. Now you can see that the limit does not agree on both sides because there's a jump. So just because f of c is undefined, just because this right here has a hole, it has nothing to do with whether the limit exists. It doesn't tell us anything. And the easiest way to prove that is just coming up with examples where it doesn't work, like I just did. I came up with 2 examples, and that doesn't work. That's the explanation for the answer. The next one says if the limit exists, does this prove or disprove that f of c being defined? It's kind of the same thing. It's neither. Okay, and I can show you an example again, just drawing this out. Let's do, let's say here. Let's say C is right here. All right, so let's just do this, this, and this. Now this one, the limit does exist because as the x values get closer to C on both sides, there is a y value to that. Whatever it is, we don't know what it is. It's just some arbitrary value. Let's just say it's 3. It doesn't matter. Either way, this one does work. So, but it does not show that f of c is defined. I could have easily made this not a hole and just colored it in like that, and then now f of c is defined. But it doesn't show it one way or the other, even if the limit exists. Okay, it could be a hole or it could be an actual point on that graph. So again, it does not prove or disprove to be the answer for that one. Very conceptual. Hopefully that makes sense with what I just said. And it is worth pointing out, if you do have any questions on anything in this video, definitely make sure you bring it up in class. This is not meant to replace all of the learning. It's just meant to be a conduit for you starting your understanding. And then if you do have any questions on any of this stuff, you definitely should ask me. So if it's not making sense, please make sure you ask. Okay, example number 5.
It says find the following limit, the limit of 5 as x approaches 3. This one's actually pretty, it's deceptively easy. So you might think, well, what am I supposed to do on this? Well, the easiest way is probably just to graph it. Okay, you might not be able to just think about it by looking at it, so I'm just going to graph it. Well, I'm graphing y equals 5. And if I graph y equals 5, it's just going to look like this. It's just a horizontal line, y equals 5. Hopefully that's a review from old school algebra on how to do that. And we're approaching 3. I'm just going to say it's 3. This is obviously not to scale, nor does it need to be. As you approach one side and the other, this is just going to be equal to 5. Okay. When in doubt, graph it out. So if you just look at this and go, whoa, I do not know how to answer this problem, well, graph out y equals 5, and you can kind of see for yourself as x approaches 3, you're going to get 5. In fact, you're going to get 5 for any value you approach because 5 is a constant. So that's basically that first section, that's subsection 1.1.1. Next section is going to be 1.1.2. All right, so this part is going to be covering the topic of evaluating limits algebraically. Okay, so the last section we involved finding limits, just basically estimating them using tables, using graphs, that sort of thing. This time it's going to be all algebraic. There's going to be a lot more non-calculator parts on this, but it is still good to check your work using a calculator while doing these problems. And I'm going to kind of show you how to do that as we go. So similar to what we were doing before, only algebraically instead of graphically and numerically. So the techniques that we're going to learn in this course or in this section anyway, for finding limits is direct substitution, factoring out technique, and rationalizing technique. Okay, direct substitution basically is where you always want to start. So it says right here, always start here. Essentially what you're doing with this is you're just plugging in wherever the value is going. Like say you have a limit problem and the value of x is going to 3 for f of x. The first thing that you're always going to want to try to do is just plug in 3 into f. Okay, I'm going to show you some example problems to kind of cement this in a little bit more. But you always want to start there with direct substitution, just plugging in that 3 directly into the function. Okay, if that doesn't work out, then sometimes you have to deal with other techniques like factoring out technique, for example. With this technique, if you do direct substitution like we were talking about in that first part, and you end up with a 0 over 0, a lot of times you can factor out what is causing that 0 over 0. I'm going to show many examples doing that in this video, so it makes more sense. And this is when you're going to want to factor. That's why it's called the factoring out technique. You're going to factor things and then cancel things out if you can. You're basically canceling out whatever's causing that 0 over 0. The last technique is called rationalizing technique because it involves having some kind of square root in the problem, and if you rationalize it, you can end up solving it as well. It usually results in a 0 over 0. That's how you know that you can use the rationalizing technique. Again, I'm going to show you examples later on this. And then once we rationalize it, a lot of times you end up doing the factoring out technique, which ultimately leads to the direct substitution. So you're just basically working your way back up that ladder of techniques to figure out limits algebraically. So without further ado, let's actually do an example. All right, so example problem 1 here, it says given f of x is equal to 3x minus 4, find the following. So we're looking for this limit right here. Okay, what I just went over before is the first thing that you're going to want to do, if possible, is you're going to want to do direct substitution. So what we're going to do for this part is we're going to plug in 1 directly into this problem. Okay, so f of 1 in this case would be equal to 3 times 1 minus 4, which is just going to be equal to -1. Another thing you could do if you really wanted is you can just throw this into a table or a graph and figure out its value that way. That's what I'm going to do right now. All right, so here I have a table for number 1 right here. Let me blow this up so you can actually see it, like so. All right, and you can see with the graph right here, so we're getting infinitesimally closer to 1, so 1 is right here. You get infinitesimally closer to it, you end up approaching -1, which is what we got when we did direct substitution. You can also use this table here, and you can see as your values get closer and closer to 1 here, 0.99, you're getting closer and closer to -1 for the f. When you get closer and closer to 1 from the other side, you get closer and closer to -1 there. So the answer is -1. So the answer is -1 based on what we were doing previously, which is the graphically and numerically. Now, if you look at this right here, you can also do direct substitution, and you still get the same answer that we would have gotten if we did it graphically or numerically. Okay, and that's the main thing that this wants to show here is that f of 1 is equal to -1. It says, what do you notice? You should notice that the values are the same. And this shows the power of direct substitution. You always want to do direct substitution first whenever you do a limit problem, because a lot of the times you end up with the answer right away. You don't have to worry about the graph. You don't have to worry about the using a table to figure out the values. Now you can still use those to show your work and show that it works, but there is an easier way with that direct substitution. Right, that's the first problem. Let's do the second example problem right here. Again, what we're going to start with is direct substitution. So I'm going to plug this in for each one of these x's right here and see what we get. So if you do that, you end up with 9 minus 3, which is 6 minus 6. So you're going to get a 0 on top if you do direct substitution, divided by, if you plug in negative 3 here, plus 3, you also get 0 on the bottom. So you end up with a 0 over 0, which is indeterminate form. Okay? When you end up with 0 over 0, a light bulb should be going off in your head. Oh, I can either factor something out or I can rationalize it. In this case, we can actually factor this out. So this is going to be the factoring out technique in action. So basically what I'm going to do is rewrite the problem, only factor everything first. That is the key. So it's going to be plus 3, x plus 3, and then x minus 2 here, and then divided by x plus 3. So right now you should be able to see that the x plus 3's cancel out. And this is what's actually causing the 0 over 0. So if you plug in negative 3 to this one here and this one here, you end up with a 0 over 0, because 0 times anything is 0. But now that we factored it out, we're just left with this part right here. So if I wanted to, I can rewrite this, which you really don't need to, but I'm just going to do it for fun. And you can write x minus 2. If you notice, there is no longer anything that's going to cause it a 0 over 0. You can just plug in using direct substitution. So factoring out technique first, and then we're going to do direct substitution here, and you end up with negative 3 minus 2 to be negative 5 for this one. So that's the answer for that first one. Now if we go back to our graph or our table, you can see this worked out fully as well. Let me get rid of number 1. Here's number 2 right here. So x squared plus x minus 6 plus 3. So you end up with this graph right here. We're looking at negative 3. So negative 1, 2, 3 right here. And you can see that there's a hole right there. It's undefined. But clearly it's going to be equal to negative 5 just based on the graph. It's approaching on both sides. It's negative 5. Another thing you could do is use it numerically. So I'm going to do like 3.01 and then just put a bunch of zeros at the end of it. You can see that this is getting closer and closer to negative 5 numerically. You also want to do the other side of negative 3, so negative 2.999. You can see that gets closer and closer to negative 5 as well. So how we're doing this is working as we're evaluating it algebraically. So you end up with negative 5 there. Okay, 1, 1, 2. We have another limit problem here. First thing you're going to want to do is do direct substitution. So you plug in a 0 for this x and for this x here, and you would end up again with a 0 over 0. Okay. This time you can't factor anything out. So hopefully you notice that. Like, oh shoot, I can't factor anything out. How am I going to solve this? What you can do is you can rationalize it. So what I'm going to do really quick is recopy the problem down. And I'm going to use rationalizing technique to rationalize this. So that way it factors out and we can figure out how to go from there. We're going to use conjugates for this. So this is really important concept you have to understand is you have to use conjugates. So it's basically a twin of whatever is over here, only instead of the minus, it becomes a plus. Okay. That's a conjugate. You should remember it from Algebra 2. It's probably been a while. So for conjugate, whatever the version is there, in this case it's minus 1, we're just going to do a plus 1. If that was a plus 1, then you would change it to a minus 1. And the great thing about conjugates is that you get a difference of squares every single time you multiply them through. So I'm going to multiply across here. You're going to end up with x plus 1 minus 1. So I squared the first one, I squared the second one, and you're just subtracting. Now if you want to do, you can FOIL that, or you can grid it out, or whatever, however you want to do it. You end up with the same thing either way. And then on the bottom, I'm going to keep this factored. I'm not going to distribute this. I'm just going to do x times root x plus 1 in parentheses here, like that. Now a crazy thing happens when you do this is this 1 minus 1 is going to cancel. So you have x over x right here. This actually is going to cancel x, and x cancels to be 1 over 1. So now if you notice, we got rid of what's causing the 0. Okay, that x is what's causing the 0 on the bottom. But now that it's gone, we can just do direct substitution and plug in the 0 right into where the x is. So we're going to do direct substitution. And you end up with 1 over 1 plus 1 is 2. So you end up with 1/2 for the answer in this one. Okay, so I just basically showed you 3 problems that are all 3 techniques for evaluating limits algebraically. So I did the direct substitution way, you just plug it in and get an answer. The second one right here, it's a factoring out method. You had to factor first and then plug it in and you get the answer. This one, there's a square root. A light bulb should go off in your head. Oh, I probably have to do some rationalizing on this one. And then you work it all out, you get 1/2. The important thing to note for all of these problems is you always want to do direct substitution first. Okay, that way you know what the answer is, or you know that it's a 0 over 0 and you have to do a little bit more work. Okay, so the key is doing direct substitution first, always. All right, the next one, example problem number 4. Okay, first thing we're going to do here, it might be tempted to go, oh, let's just factor this out. It looks like something to factor. I would not do that. I would do direct substitution on this right away. So I'm going to plug in -2 for x there. You're going to get 4 plus 1 is 5 up top. On the bottom, you're going to get 3 times 4, which is 12. 12 minus -4, 12 plus 4 is 16. 16 plus 5 is 21. The answer for this is just 5 over 21. There's nothing that cancels. There's no 0 over 0. It's just straight up direct substitution. The next problem, I'm going to do direct substitution again. And you're going to end up with 8 minus 8, so 0 on top, divided by 2 minus 2, 0 on the bottom. So this one is going to factor out. Okay, there's no square root, so we're not going to be rationalizing. So a light bulb should be going off in your head. Oh, I'm going to have to factor some stuff out. So for this top one, I'm going to factor out a 2. The bottom one just stays as x minus 2. I can factor that difference of squares on top. X is going to 2 here. Factor out the x squared minus 4 here to be x plus 2 and x minus 2. Okay, you should recognize how to factor that from quadratics from previous math classes. If not, you are behind in your math. You're going to want to review how to factor quadratics for this course. X minus 2 is going to cancel here, and now you're left with 2 times x plus 2. Now what we can do is just do direct substitution on this, and you end up with 2 times 4 to be 8, and the answer for this one is 8. All right, so for this next one, you'll notice there's a square root in it, so it's a sign that you're probably going to do rationalizing technique, but still hold true to the plan and plug in the direct substitution first. You plug in -3, you end up with the square root of 16, which is 4. 4 minus 4 is 0 on top. Plug in -3 on the bottom, you get -6 plus 6, so that's 0 over 0 as well. So a light bulb should be going off in your head. Oh, I'm going to need rationalizing technique for this. So first thing I'm going to do, I'm going to rewrite it. So the limit as x approaches -3, and we're going to multiply it by that conjugate. And if you notice, it's root x plus 19 minus 4. So I'm going to multiply this by root x plus 19 plus 4. So right here like this, and I'm going to write that in really quick with the conjugate. Plus 4 this time. Same thing with this one. Plus 4. Okay, now from here, you're going to end up with the following. The limit as x approaches -3, you're going to have x plus 19 minus 16 over, I'm going to factor out this 2x plus 3, or 2x plus 6 to be 2 times x plus 3 times the square root of x plus 19 plus 4. Let's put a line there. Okay, and a really interesting thing happens here. This cancels here, so you end up with x plus 3 on top, which is going to cancel with this x plus 3 right here. That's why it's important you factor everything. Then you're going to have 1 over that entire mess on the bottom. But the great thing about this is we got rid of the thing that's causing the division by 0, namely that x plus 3. This was causing a division by 0. Now that it's gone, you're not going to divide by 0 anymore. So now you'll actually have an answer. So it's just going to be 1 over 2 times, so this is the square root of 19, x plus 19 here. So that's going to be square root of 16 is 4. 4 plus 4 is 8. So it's going to be 1 over 2 times 8. So your final answer should be 1 over 16 for that third one. Sorry, things got a little crammed there, but hopefully you can kind of see the answers for all of these. Let's see, this one was 8. I wrote it right here. And then the other one is right here for that answer. Okay, onward to number 5. Okay. Sometimes they give you problems in a calc class where they don't even have an equation. It just gives you what the limit values are, and you have to evaluate some limit expression like this one right here. Okay, it's the same kind of rules. Do direct substitution first. So then you're going to end up with f of -5 plus 3 times g of 5. Okay. Well, f of -5 isn't given in this problem, but we have x is approaching -5 in for this f right here. So this one right here, if we do direct substitution, you know that f of -5 is equal to 4. Okay, now you don't actually really know that. We're kind of just making an assumption here that you can do direct substitution on this, but for the intent of actually solving this problem, it does actually work here, where you can just put a 4 here. Plus 3 times g of 5, which it's really the limit of g as x approaches 5. Either way, it's still 5. So you end up with 4 plus 15, which is 19. Your answer should be A for that one. Okay. Whenever you see these are usually a little bit easier than the ones because you could just basically do less math. There's not, this was just basically direct substitution for that problem. When you see a problem like this with a complex fraction, it gets a little bit more complicated, but it's nothing that bad as long as we simplify it. It ends up not being too difficult. I'm going to show you a little trick on how to simplify this in an easier way. I want to get rid of this denominator here and this denominator here as well. And rather than doing common denominators and then multiplying by the reciprocal and that whole mess, what you can do in one foul swoop is just multiply the top and the bottom by both denominators. Okay, so then when you do that, you end up with the following. Okay, so we're just going to distribute that out. Okay, so you're going to end up with 2 minus x plus 1, because the 2's are going to cancel. You leave that in parentheses there, divided by, 2 times x plus 1 times x minus 1. Okay, this doesn't really simplify too much yet, but if we break this down a little bit, so this is going to be negative x, and then 2 minus 1 is 1. So I'm going to cancel all this out. You end up with negative x plus 1. Now, if you notice, it doesn't really match with what we have down here, but it's the opposite of what we have down here. This one's negative x plus 1. This is positive x minus 1. So what you can do is actually factor this out, cancel here, and that's just negative 1 over 1. Okay, now we got rid of what's causing the division by 0 because we got rid of that x minus 1. So now we can just do direct substitution with with this 1 right here and just plug it in right there. So you end up with negative, because of this negative 1 right here, divided by 2 times 1 plus 1, which is 2. So you end up with negative 1/4 as the answer for this problem. So the main thing is, it's a complex fraction. You don't want a fraction over a fraction, so multiply it to get rid of the denominators. If you notice, after I do this red step right here, the orange step is just similar to all the other problems that we've done already. It's just that extra step of getting rid of the denominators to make the problem solvable. Okay, onward to example problem number 7. Same kind of thing with a complex fraction. We have this fraction on top of a fraction here. So what we're going to do is multiply the top and the bottom by that denominator. So I'm going to multiply by x plus 2 over x plus 2. I guess first thing I should do is try to do direct substitution. And if you do direct substitution, you end up with a 0 over 0. Same with this problem that I just did over here. If you do direct substitution on that, you end up with 0 over 0. So that's how you know that you can solve it with some rationalizing or some factoring technique. But anyway, this one would also get you a 0 over 0. And we're going to multiply both sides by that x plus 2. So you're going to end up with the limit as x approaches negative 3. And you're going to have 1 plus x plus 2 on top, divided by x plus 3 times x plus 2. Okay. From here, you'll notice this top one all simplifies to x plus 3 because the 1 and the 2 just combine there. And then now you can actually just get rid of this and this. So it's 1 over x plus 2. You do direct substitution because we got rid of what's causing that division by 0. Right there with that x plus 3, it causes that division by 0. Since it canceled out, we can just do direct substitution, and you end up with 1 over negative 1, which is just going to be equal to negative 1. Okay, number 8. This one has 2 values. You're still going to want to do direct substitution on this. It's got 2 parts of the expression, I should say. So we're going to plug in a 3 for this one. Now you have 1 over 0. Uh-oh, that's a problem. That would be normally infinity because you're approaching 0, or negative infinity, or does not exist. It really depends on what the graph looks like. And then we have this one over here with 2 x's in here as well. If you plug in the 3 here, you also get a 0. So you're dividing by 0 on both of these. So you end up with 1 over 0 minus 4 over 0. Okay. Either way, you can't do any math on this. Okay, so the long story short of this is if you ever have a problem like this, what you need to do is simplify that rational expression as much as possible. So what we're going to do is we're going to get common denominators. And to do that, I'm going to first rewrite this. So now it's going to be 1 over, I'm going to multiply the top by x plus 1 and the bottom by x plus 1. So now it's common denominators with this one right here because this whole thing right here factors to x plus 1 times x minus 3. Okay, so essentially what I'm going to do, let me get rid of all this to clean it up. Essentially what I'm going to do is just factor everything first, and then it's going to be a little bit easier to see. So we're going to do x minus 3 minus 4 over x minus 3 times x plus 1. Okay, of this whole thing, we're doing the limit for it. Okay, what I'm going to do is multiply. If you notice this one right here, it's missing from this denominator here. So I'm going to multiply the top and the bottom by this x plus 1. And I'm going to rewrite it over here. So you're going to end up with the limit as x approaches 3 of x plus 1 minus 4 all divided by x minus 3 and x plus 1. I'm going to keep everything factored because a lot of times that ends up canceling out. I'm going to simplify that top part there, which is just x minus 3 divided by x minus 3 times x plus 1. Now you'll notice here that the x minus 3's we're going to cancel. So now you can just do direct substitution on that. You got rid of what's causing the division by 0, which is that x minus 3. Do direct substitution, you end up with 1 over 4 for the final answer. Okay, number 9, the last one we're going to do in this section. First thing you're going to notice if you do direct substitution, 1 over 0 plus 5 over 0. Okay, indeterminate form, that means infinity plus infinity. Is one of them a negative infinity? What if there's a DNE? We don't know. So the main thing is we need to combine those using common denominators. That's the first step that I'm going to do, so we can kind of get a better look at what's going on here. I'm going to multiply the top by x minus 5 and the bottom by x minus 5. So now if you notice, I have common denominators for these right now. So what I'm going to do is combine the numerators. We're just going to add across, add the numerators up, and you end up with x on top divided by x times x minus 5. Plug in the 0, you end up with 0 over 0, but if you cancel this out with this, you get rid of what's causing the 0 over 0. Now you can do direct substitution, you end up with 1 over negative 5, so negative 1/5 is your answer. So that's a bunch of problems involving evaluating limits algebraically. If you have any questions on anything, definitely let me know and we can kind of go over it. This was a lot, but the main thing is those 3 limit evaluation techniques. I would kind of follow them in order. Always start with direct substitution. If you end up with a 0 over 0 and it can factor, then use factoring out technique. If you end up with a 0 over 0 when you do direct substitution and there's a square root in there, then you're probably going to do rationalizing technique. But yeah, if you have any questions on anything in this section, definitely let me know. All right, I do want to also point out, based on that last section that we just did, finding limits or evaluating limits algebraically, you could have solved all of those with graphing as well. Okay, it's just that sometimes, you know, your tests or quizzes, your assessments are going to be non-calculator, so you are expected to actually do them by hand algebraically as well. But like for number 2, you can graph this out if you wanted, and then figure out what's going on at negative 3. Find the graph here. You'll notice it's undefined, but you can see it is negative 5. You can also do it numerically, where I can put in, you know, a bunch of values. You can see it's getting closer and closer to negative 5 here. If I wanted, I could do, you know, 2.99999. It's getting closer to negative 5. Okay, number 3, same kind of thing. It was the one with the square root here. I'm going to blow this up a little bit. Square root of 1 minus 1 over x. If you notice at 0, it's undefined. I try to put my graph over it, says undefined, but if you actually scroll in, you can see that it does cross at 0.5. It's getting closer to 0.5 on both sides. I can find the limit here as well. Whoops. Get closer to 0 on both sides. I can make this negative. You'll also see the 0.5. That next one, 4a, looking at the graph here, if you plug in negative 2 right away, direct substitution, you get 5 over 21, which is what we got when we did it algebraically. That next one, the 2x squared minus 8 over x minus 2. If you plug in 2, you get undefined here because it causes a 0 over 0, if you recall. But if we look at the graph here, we're getting closer and closer to 2, which is right here. It's undefined. But you can see right here that it's this value, whatever this value is right here. So 5, 6, 7, 8. So it is 8. That is what we got. Also, if you plug in a value like 2.1 and put zeros in it, you'll notice it's getting infinitesimally closer to 8. So that works. If you wanted to as well, you can change this to 1.999. You'll still get, it's an approaching 8, so that value as well. For C, same kind of thing. If we look at the graph, we're going to have to zoom out a little bit on this one. We're getting closer to -3. So -3 is right here. You'll notice that it's undefined. That one's actually kind of hard to see with the graph, so it's going to be easier if we just plug in a value that's getting closer and closer to 3. And you'll notice it's 0.625. We got 1 over 16, where if you do 1 divided by 16, you end up with 0.0625, so it does show that it was 1 over 16. The next one, number 6. So I'm skipping number 5 because it didn't really involve much calculations. Number 6 right here, it's got that complex fraction. It's undefined at 1, but if you put a 0.1 in here, make a bunch of zeros, you can see that it ends up being closer to -1/4, which is what we got. You can also look at the old graph here of what's going on at 1. You can kind of see that it's, you know, getting closer to -0.25, I'm sorry, on both sides. Number 7, same kind of thing. You plug in -3, you get undefined. You can plug in -3.1 with a bunch of zeros at the end of it. It's getting closer to -1. You can do -2.9 repeating, getting closer to -1. You can just plug it in using the graph as well, getting infinitesimally closer to -3. You can see numerically you still get that -1, which is the value we got. Number 8, you plug in 3, it doesn't work. Plug in 0.1, put a bunch of zeros, you get 1/4 there. The last one, same kind of thing. Plugging in 0 doesn't work, but just do 0.1 with a bunch of zeros at the end of it. You get -1/5. You can make it negative to see that it matches on both sides. Just look at the graph here as well and see. So you can solve all those that we just did, where it says evaluate algebraically. You can still solve those if you just use a graph or numerically as well. Just wanted to show you that it's all related. Everything that we've done is still completely related. It's just different techniques to find those limits. All right, so this next section is going to be all about one-sided limits, which are the exact same thing as just regular old limits, only it's actually half the work, so it's actually easier, which is kind of nice. One-sided limits kind of take advantage of the notation. It's kind of a new notation that we haven't really experienced yet, where you're actually putting a sign in the upper right corner of wherever the x is approaching. So if it's a positive, it means it's the limit from the right. So it's one-sided, but it's a limit from the right. An easy way of thinking about that is if you have a number line and you have a 0 on the number line, on the right, there's a positive. On the left, there's a negative. So if there's a positive there, that means you're approaching from the right. The negative version of it, so if there's a negative here, it's approaching from the left. It's as simple as that. You don't need to worry about the limits matching on both sides because it's just one-sided. There isn't both sides to deal with. That's why I said it's like regular limits, only it's half the work, which is nice. This next one, it says limits exist if true. Okay, you should know this already, but basically it's saying if the limit from one side is equal to the limit from the other side, it's equal to the limit on both sides. If you notice, this one is just plain old C, this one here has a negative, and this one here is positive. So if the limit on one side matches the limit on the other side, then it matches the limit on both sides. That's what essentially that's saying. That should be pretty straightforward, pretty easy to understand because we've gone over it before. It's just now introducing a new notation on top of that other stuff we were talking about before. If you remember from section 111, if limits do not match on both sides, the values don't match on both sides, then the limit does not exist. So this is just saying it exists if true, if this whole equation here that I have is true. Limit does not exist if this is true. So if the limit does not match one side or the other, then it's not equal to the limit altogether because this is a double-sided limit. This is just one-sided and one-sided there. And then the limit does not exist. If you remember, Lindsay Lohan from that Mean Girls movie talked about that. And limit doesn't exist because it didn't match on both sides. So that's what that basically is showing. To kind of cement this, let's do some example problems. So right here it says 113, example problem number 1. We're finding the limit as x approaches 1 from the left. Okay, so here's x equals 1 right here, and we're approaching from the left. What value is it approaching? 4. So the answer for this first one is going to be 4. The next one is it's approaching 1 from the right, so here's approaching 1 from the right. What's that value? -2. So the answer for that other one is -2. Pretty straightforward, just looking at the graph. The next one, example problem 2. Holy cow, there's an A through K on this one, so tons of example problems, but this will be fun. All right, so first one, it says it's not even a limit, it's just straight up old algebra. F of negative 2, well, this is just going to be equal to F of negative 2, which is right here. Here's negative 2. The F value is going up to positive infinity, so we're just going to write undefined for this one. So there's no actual value, it's just going up, or an asymptote. The next one, what's the limit as x approaches negative 2? Well, on one side, it's infinity. The other side, it's negative infinity. So this one's actually going to be a DNE. You do not want to get undefined and DNE mixed up. They are two totally different things. So don't mess that up. Negative 2 from the left, that's this part right here. If you notice, it's negative infinity, so I'm going to put a little negative infinity in there. F of 0, that's just straight up algebra. F of 0 is right here, 4. The limit as x approaches 0, okay, so we're approaching 0 from this side and we're approaching 0 from this side. It does not agree on both sides, so that's going to be a DNE. F of 2 is undefined. There's no islands anywhere where that exists, so we're just going to write undefined again. If you want, you could just write this. It's probably easier to do it that way. G, you're approaching 2 from both sides, approaching here, approaching here. It doesn't matter that there's a hole there. This looks like it's going to be about 1/2. 0 from the left, right here, is also going to be 1/2. F of 4, it's right here. We don't look at this because that's going to infinity. It's just the actual spot right there. That's going to be 2. J, as you approach 4, that's going to be positive infinity. So you're approaching 4 here on this side and that side. And last but not least, 0 from the right here, and you end up with 4. Okay, so it's just understanding the notation, what it means, and being able to read graphs. So that's what essentially that's doing right there. Number 3, okay, here's a multiple choice problem. It says, what is the limit as x approaches 2 from the right? So here's 2 right here. We're approaching from the right. The answer should be 3. It's pretty easy. Example problem 4. Okay, this one gets a little trickier because you end up with a square root of a negative on one of these. Namely that first one, A, it says the limit as x approaches 3 from the left. Well, if x is approaching 3 from the left, that's values like 2.99999 and so on. So if you subtract that 2.99 repeating minus 3, you're going to have a square root of a negative. There are no imaginary numbers in calculus, not this class anyway, so we're not going to deal with anything like with imaginary numbers, complex numbers, that sort of thing. So this one's just going to be DNE, okay, because you can't do the square root of a negative. This one, however, if you have x is approaching 3 from the positive side, that's 3.000, a bunch of zeros with a 1. So now it's the square root of a positive value. It's just going to end up being 0 because this is really close to 3, and 3 minus 3 is 0. Because you do have to be really careful with one-sided limits. You don't want to just do direct substitution right away because sometimes it gets you a false positive. For example, if I did direct substitution on part A and just did 3 minus 3, well, that's 0. But it's not 0, it's DNE. So that's kind of how that works. To kind of cement this in a little bit more, I'm going to show you the graph. So here's the graph for that one right here. If you notice, there is nothing on the left side of it. So you can approach from one side, from the right, but not the left, because there's nothing there. The limit would be DNE for that one. So hopefully the graph kind of makes more sense with it. It doesn't get less than that 3, because then you have imaginary numbers. Okay, so that's the answer for those two. Uh-oh, piecewise, everyone's favorite thing from algebra. I'm kidding. Okay, so these aren't actually that bad, as long as you follow directions and pay attention to what you're looking at. So it's 2 from the left. So that means it's less than 2. So that means you have to use the first piece when solving this problem because it's 2 from the left. Now what you can do is direct substitution on this. So just do direct substitution with the 2. You get 8 minus 3 is 5. 5 is the answer for that one. Okay, we're going to do the same thing with the other one, only this time it's 2 is greater. It's the right side of 2, so it's greater than the 2 there. So we're going to have to use that second piece. When we use the second piece, we're going to plug in the 2 there. It's 2 minus 3 is negative 1 squared is positive 1. So the answer for that one is positive 1. Now it's the semi-tricky part where now you have to use both pieces. Well, all you have to do is check, is this equal to this? It's not, so then it's DNE. Okay, so if you're like, wait, which piece do I use? You have to use both of them because you have to approach 2 from both sides, the less than 2 and the greater than 2. It doesn't matter if it's equal than 2 because you're approaching, so you don't need to worry about the x equals 2. It's just approaching from both sides. These do not agree. So these do not agree. And if that's the case, then it's DNE. Okay, we kind of went over that before in the previous slide right here. Oops, right there. Limit is DNE. Limit does not exist if true. Okay, in this case, it's not true. It's not equal on both sides. Hopefully that makes more sense. Okay, number 6, the last one here. Now we have a 3-piece piecewise function. This is crazy, but again, it's the same kind of principle here. All we're going to do is figure out which piece do we use if it's 1 or -1 from the left. Well, that's less than -1, so we're going to use this first piece here. Just do a little bit of direct substitution on that. You get -1, -1, which is +1, -2 is -1, and that's the answer for that one. Okay, now to kind of show you these last couple problems, I guess we'll start with 5 first. I'm going to graph it really quick to kind of show you why it's 5, it's 1, and then it's DNE. Because again, it's one thing to be able to answer these and make sense of them, but it's another thing to paint that picture in your head of what this looks like. So that's what I'm going to show you right now, is what all this looks like. Okay, so number 5 here, we have this piecewise function right here. Let me rezoom it right here. Okay, as you approach 2 on one side, you end up with about 5, as you can see. And then if you approach it from the other side, you end up with about 1, which is what we got. But if you notice there's a jump there, and if there's a jump, the limit does not exist. So that's why number 5 plays out like that. Number 6 was 3 pieces. So we have this line here, this point, and then this like cubic function at the end here. And we are looking for what's going on at -1 from the left. So we're approaching from this side right here. We're just approaching it, seeing where kind of like dead ends right here at the end here. And it looks like it's -1, which is the value that we did get. Okay. It is important to understand you could do this numerically as well. It's just kind of easier to see one-sided limits using the graph. So hopefully that makes sense. So that section is all about one-sided limits. Hopefully you realize it's just half the work, so the problems aren't that bad. But just mind your domains. Make sure you're not doing the square root of a negative or anything like that. So that's basically one-sided limits. Definitely let me know if you have any questions. All right, this next section is all about asymptotes. And if you thought that Algebra 2 was the last time you were going to see asymptotes, unfortunately, that is not the case. But what's great about limits is it kind of ties together all the ideas of asymptotes and kind of defines them a little bit easier. So using limits to define asymptotes is basically the main thing that we're going to be doing. In this section, we're also going to be finding vertical asymptotes and finding horizontal asymptotes using limits. So first thing we're going to do is start with right here. It says inquiry problems. So just problems to get you to kind of think a little bit. And it says, how are one-sided limits related to vertical asymptotes? So the last section was all about one-sided limits. How are they related to vertical asymptotes? So I'm going to kind of show you what this looks like. So I'm going to graph out a vertical asymptote. Let's just say we're going to do it at point, I don't know, x equals c. It doesn't really matter. So we have an asymptote here, an asymptote there. I guess it's just one asymptote right there at x equals c. How are one-sided limits related? Well, if you notice on either side, if you approach from one side, it's positive infinity, or if you approach from the other, it's negative infinity. Okay, I could have had them both go up like this, like kind of similar in the last section that we covered. They could have both gone up to positive infinity. I could have also had them both go down to negative infinity. If I wanted, I could have done that. The moral of the story is, if you have a limit problem and you're approaching some value c, whether it's the left side or the right side, it doesn't matter, your answer is either going to be positive or negative infinity every single time there is a vertical asymptote. That's the main thing I want you to see on this, is if you do a one-sided limit on these, it's either going to be positive and negative infinity each time. Otherwise, it's not a vertical asymptote. Okay, so that answers that first part. And we're going to go into more deep dive into this in a little bit, but just kind of wanted to show you that the main thing is asymptotes go to infinity or negative infinity at vertical when it's a vertical asymptote. The y value goes to positive infinity or negative infinity. Limits can kind of help show you that. And then the next one says, how are one-sided limits related to horizontal asymptotes? So what I'm going to do is graph this out as well. And we're going to have this graph go to, and we'll just say point B here. Okay, and then this is just going to be the horizontal asymptote here. And then I'm going to graph some graph that looks like, I don't know, doesn't matter. I'm just going to go like this and then like this. Okay, there's a horizontal asymptote right there as, you know, at b, at y equals b. I could have had this go up like this too and done this, something like that. You'll notice it's a horizontal asymptote in both directions. The main thing I want you to see is it's how are they related to horizontal asymptotes. The main thing I want you to see is you have to take the limit to infinity or negative infinity, okay, of f of x, and that's going to be equal to whatever the horizontal asymptote is. In this case, it's b, and it's also if you go to the negative infinity for the x. Still going to be equal to b. Okay, so the moral of the story is one-sided limits help you find horizontal asymptotes because it's one-sided, you're going to infinity. Positive infinity is one-sided. Negative infinity is one-sided. So the question says, how are one-sided limits related to horizontal asymptotes? You can answer it as something like, well, if you have x going to infinity, it helps you find the horizontal asymptote, if there is one. Or if you have a limit as x goes to negative infinity, for some function, you can figure out the horizontal asymptote if there is one using that as well. So that's how they're related to one-sided limits. It helps you find those values. Let's go to the next thing, which basically just sums up what I just said. Horizontal asymptotes are found if you have x going to infinity or negative infinity. You end up with these horizontal asymptotes. It's always y equals for each of them. So make sure you do that every single time you find one. You have to actually make it where x is going to infinity, and once you do that, the answer is going to be y equals because it's a horizontal line. Y equals whatever value always ends up with a horizontal line. Should know that from previous algebra classes. Vertical asymptotes, on the other hand, it's similar to what I already wrote before. From the left side or the right side, it's either positive or negative infinity, depending on the flavor of asymptotes that you have. Sometimes they go in the same direction, sometimes they go in opposite directions. Either way, if you end up with a infinity or negative infinity, there's a vertical asymptote going on there. These always have x equals because they're vertical, so make sure you don't mess that up. X equals is vertical asymptote, y equals horizontal. Okay, I saw this joke online. I thought it was pretty funny. You know, if you like math humor, I guess it's funny. It's just kind of playing up the fact that the 8, if you tip it over, it looks like an infinity. So it's saying if the limit as x approaches 8 from the right of 1 over x minus 8 is equal to infinity, because you're just tipping over the 8, then does the limit as x approaches 5 from the right of 1 over x minus 5 equal to the 5 tipped over. So basically tipped over the 8 and acting like that's an infinity, and then tipped over the 5. Obviously that's not the case because there's no such thing as a tipped over 5 like that. I just thought it was kind of funny, so I included it in this. Hopefully you got a chuckle out of it. All right, 1, 2, 1, example 1. So let's do some more example problems here to kind of solidify our understanding of what these asymptotes are all about. It says if a continuous function is f and the domain is x is greater than 0, so it's only positive values. If the asymptote is x equals 0, so main thing that you have to notice here is this is a vertical asymptote because it's x equals. The other one is y equals 2. That's a horizontal asymptote. So one's vertical, one's horizontal. Which of the following must be true? Okay, so an easy way of thinking about this is with vertical asymptotes, remember it's always the limit as it approaches some value. In this case it's 0, either the positive side of the 0 or the negative side of the 0 for this function here. It should be equal to positive or negative infinity. Okay, I could write the exact same thing down again, only from the other side. It has to be equal to positive or negative infinity. So real quick, what I can do is look in the multiple choice and say, you know, does any of these match? Okay, are these existent in any of these problems? Okay, we have this limit here with 0, 0 here, and this as well. Okay, but we want it to be positive or negative infinity. This one does not work. This one doesn't even have a 0, so it can't be D. So right, just from doing that first part, the x is approaching 0 from both sides, you can see that it's not going to be B or D. Okay, we're going to do the exact same thing with the y equals 2. Okay, remember for horizontal asymptotes, it's the limit as x approaches infinity. I'm just going to write positive or negative infinity of f of x, and this has to be equal to 2. So now we have to see, are there any values where this works? This one is approaching 2 when you get infinity. That's the opposite of what we have. We don't want that. We want it to be where it's x approaching positive or negative infinity is equal to 2. So it's definitely not A. This one, boom, actually shows what we just wrote here. So the answer for this one is C. All right, let's go to number 2. If x is greater than or equal to 0, the horizontal line y equals 2 is the asymptote. So it's y equals 2, it's a horizontal line. So it actually says it's a horizontal asymptote already. Which of the following must be true? Like we said before, you have to do the limits as x goes to positive or negative infinity, which only one of them even has that, of f of x. And it's supposed to be equal to 2 because it says y equals 2. Well, that's definitely E. The other ones don't work. That would be like a vertical asymptote. This one could be a hole. It doesn't necessarily have to be a asymptote. The other ones don't even have infinities in them, so it's definitely not those. E would be the answer for this one. All right, 1, 2, 1, number 3. All right, so we have 3 graphs right here, and it says which of the following limits are equal to -1. Holy cow, lots to go over here. First thing we're going to do is this one right here. So we have the limits as x approaches 0 from the left of the absolute value of x over x. The most important thing that I want you to see on this is like x over x is just going to be 1. But in this case, it's the absolute value of x. And we don't know what that is, but we know it's positive. So you have a positive of some value, in this case something closer to 0, close to 0 from the left, divided by that same value, only it could be negative. In this case, it actually is negative because it's the left of 0. So essentially we have the sum value divided by itself, but one of them is the positive value and the other one's the negative value. So in essence, you just end up with -1 because of that. So definitely not Roman numeral number 1 is an answer. So it cannot be C just based on that. Another way of looking at this is if you actually graphed it. You can kind of see right here what the graph looks like. We're approaching from the left, and you can see it ends up being -1. It's undefined there, but you're approaching it, so it's approaching -1. So anyway, that one's -1. So that one is one of the answers. Cool. The next one is we have this right here. Try direct substitution right away. You end up with 0 over 0. So that means that something's going to factor out. We can do factoring technique for this. Same thing that we went over in 112. It's all, remember this, all this stuff's related, so we're just throwing it all together here. Divided by 3 minus x. Okay. The x minus 3 and 3 minus x will cancel to be -1, so I'm just going to put a -1 in here. And then you have x minus 4 over -1. You can do direct substitution now, so again, it's throwing it right back into that stuff from 112 that we went through. 3 minus 4 is -1, divided by -1 is +1, so it's definitely not going to be Roman numeral 2. So it cannot be this, so it's between these two now. Okay, the last one, x is going to infinity. Okay, this one's a cool problem to do because anytime you go to infinity, it makes all the math super easy to do. I'll kind of show you what I mean right now. Okay, when you're going to infinity, any number that's with it, any constant, is meaningless. So for example, right here, this 1 minus x. Well, x is going to infinity, so it's 1 minus infinity. Well, 1 minus infinity is just going to be -infinity. That 1 is meaningless. Same with this right here. 1 plus infinity is still going to be infinity. It's like if Elon Musk, richest man in the world, billions of dollars, it's like if he lost a penny. It's meaningless. Only this is way more than what Elon Musk has because it's going to infinity. So it keeps going. It goes way past a billion, way past a trillion. It just keeps going and doesn't stop. So the moral of the story is you don't actually need this and you don't need this. Okay, because it's meaningless compared to the x that's going to infinity. You couldn't do this in the other problems because x was going to 3. So all those other values are actually meaningful because 3 is not infinity. But 1, this 1 is meaningless because you're going to infinity. It's forgotten about. So you just have -x over x, that's just -1. There's not much other math to really do on that one, which shows that that's the horizontal asymptote, y equals -1. Okay, I have the graphs for these other ones as well. Here is that Roman numeral 2 here. You can see as we approach 3 here, let's approach 3. From this side, you end up with undefined. But if we actually had the values shown, you can kind of see what it's actually equal to. At 3, you can see that it's getting closer and closer to that 1 value right there. So that's why that's equal to 1. I could also write 3.0001. It gets closer and closer to 1 from that. This other one right here, we're going to infinity on this. So let's graph this. You can kind of see as you go to infinity, it just kind of flatlines at -1. If I wanted to, I can actually graph y equals -1, and you can see that's getting closer and closer to that value right there. In fact, if I zoomed in right here, you can see it looks like it's right over it, but it's not. It's just that when you're zoomed out, it looks like that. But you're getting closer to -1 on both sides. You could also put an infinitesimally bigger value in here. So if I plug in 1, it's 0. I'll plug in 10, 100, 1,000. Just keep going with this. You end up with -1. You kind of see that pattern there. So that's why that one's equal to -1. So long story short, this one also does work. So the answer for this one should be B. Onward we go. Example number 4. All right, so here's another example. Example number 4, it says a table above shows, okay, the table is actually right here. It shows selected values of a continuous function. Okay, so it is important to understand that it is continuous, means there's no holes, jumps, or gaps. There's no asymptotes. There's none of those discontinuities that we talked about before. There's no discontinuities. It is a continuous function. You should be able to draw the function without lifting your pen or pencil off the paper. That's basically the definition of continuity. We're going to talk about it in a little bit more detail in the next section, but for this one, we just need to know that it's going to be a connected function. For 0 to 13, what is the fewest possible number of times f of x is equal to 4? So to kind of answer this, I am going to just straight up graph this. I'm going to plot these points out right here for this continuous function. So 0, 3. Okay, so I'm just going to put it maybe like right here. So 3, 0, 3. 4, okay, so I'm just going to put a little 4 here, 4.5, so maybe 4.5 is right here. It is important to note that this does not need to be to scale to answer this question. You can still totally answer it without putting it to scale. In fact, it's a little bit easier if you don't really worry about the scale so much. 6, 3. Okay, the next one, 8, 2.5. I'm going to have to make a 2.5 in right here. Plot that point. And then 13, 4.4. 13, and then I'm going to put 4.4 right here. And we're going to plot that point. So here is all those plotted points for that continuous function f of x. And it is important to note that you do have to connect all these dots. It doesn't matter how it is because it doesn't actually pertain to that. But it's basically saying what is the smallest or the fewest possible number of times f of x is equal to 4. So what I'm going to do here is I'm actually going to graph y equals 4. And it's just going to be a horizontal line here. So something like that. Okay, we're looking for the fewest number of times that f of x function, the function that's the red dots, basically crosses that 4. We want the smallest amount. So I'm just going to draw a continuous function that would get us the smallest amount. So I'm going to do this, just basically connect the dots, and we have something like this. And you can see that it connects, or crosses, I'm sorry, this y equals 4 3 times. So the answer for this one should be 3. Okay. It is important to note, though, that it is asking for the minimum. Okay, it could have asked for, well, it couldn't really ask for the maximum, but if I wanted to, I could do the maximum on this. And essentially, you can just do it, as many times as you want here, where now it's intersecting, it's still going through all the dots, but I'm going up and down on that line multiple times. That's why it's asking for the minimum, because it's just the smallest amount of times it goes through, something like this, and it's 1, 2, and 3. So the answer for this one is 3. Now this one doesn't really need to be on this section 1, 2, 1, since 1, 2, 1 is all about asymptotes, but it still is a good problem to understand and make sure you know how to do. Basically all I did was graph the points. I didn't even use limits really to solve this. I just used the fact that it was continuous to figure out that it was 3. All right, and the last one here is got a lot of problems on it. That's okay. So this first one, it says find the limits, the following limits. We're going to, first thing you should do is plug in 2 just directly into this. So if you plug in 2 directly, you're going to get a 5 on top. On the bottom, you're going to get a 4 plus 2 minus, so it's 4 plus 2 is 6 minus 6 is going to be 0. So you end up with 5 over 0, which means you have a non-zero over a 0. That means a vertical asymptote is happening. That is important to understand. A vertical asymptote is when there's a non-zero over 0 occurring. That's what's happening at every single vertical asymptote. If it's 0 over 0, then that's a hole, but that's a whole other story that we don't need to worry about right now. So 5 over 0, we just need to figure out, is it an asymptote that's going up like this? Is it going down? Is one going up and the other one going down, or vice versa? We just need to figure out what flavor of asymptote this is to figure out, is it positive infinity or is it negative infinity? Anytime there's a vertical asymptote, the limit should equate to a positive or negative infinity, or DNE, but this one's actually one-sided, so there is going to be an answer to this. So what we're going to do basically is just figure out the sign. Is it positive infinity or is it negative infinity? In order to do this, we're just going to plug in this 2 value here, but we're going to plug in a value that's getting closer to 2, but that's bigger than it. So I'm going to plug in 2.1. If I plug in 2.1 into this, you're going to get 5.1 on top, which is positive. If you plug in 2.1 on the bottom, you're going to get a value bigger than 0, slightly bigger than 0, which means that it's positive. So it's positive over positive. That means it has to be not negative infinity, but positive infinity for a. So a should be positive infinity. B, first thing you want to do is plug in 0. If you plug that in, you're going to get 0 squared, which is 0, minus 1 over 0. Okay, well, the 0 is easy. We just need to figure out about that 1 over 0. A light bulb should be going off in your head. That's a non-zero over 0. So that means it's a vertical asymptote, which means it's either going to be positive infinity or negative infinity. We just need to figure out which one it is. Well, the 0 is we don't really need to worry about, so this one's just kind of gone. We need to figure out this part right here, though. Is that going to be a positive infinity or negative infinity? Well, there's a negative in front of it, so we have to take that into account. So it's 0, or it's negative 1 over 0 there. So we're plugging in a value that's to the left of 0. So let's just do negative 0.1 for the x value that we're going to plug in. If you plug in a negative 0.1 into this, you're going to get a negative negative, which is a positive. So b is also going to be positive infinity. Okay. It is important to note that if you really wanted to, you could also just graph these and see what's going on in the graph, but I'm showing you the non-calculator way in case this is a non-calculator problem on an assessment. All right, the next one. This time we're having x go to infinity, so a light bulb should be going off in your head that this involves a horizontal asymptote. If you have x going to infinity, this 2 remains unchanged, but this one right here, it ends up being 3 over infinity. Okay, and the easiest way to think about 3 over infinity is if you had 3 pizzas and you divided it up infinitely many times. So if you had 3 pizzas and you want to divide it up by infinitely many people, how much pizza does each person get? Well, if you have 3 people divided by 3 pizzas divided by infinitely many people, everyone's basically going to be getting 0 pizza because you're dividing it up infinitesimally time. You just keep cutting it up more and more and more. Eventually, you're going to get to the molecular and atomic scale. So it's not really even pizza anymore. But this is math land, and we can just kind of make this stuff up with our understanding. So imagine you're dividing up pizza infinitesimally more and more and more. You end up with essentially nothing. So it's 2 plus nothing is 2. So the answer for C is just going to be 2. The next one here, we're going to infinity again. And what's great about infinity, we talked about this a little bit earlier, is this 1 is basically meaningless. We can just kind of ignore it, okay? Because you have infinity squared plus 1 on the bottom. That plus 1 is meaningless. Again, it's like Elon Musk losing a penny. He wouldn't even know. We're going to infinity, which is way more than billions and billions of dollars. So we can just get rid of that 1. Now you have x over the square root of x squared. Well, the square root of x squared is just x. X over x is 1. So the answer for part D would just be 1. Okay, the next one here, where x is going to infinity again. So you can kind of get rid of these 1s here. Those are meaningless. Another thing you can do is the infinity to the 4th power is so much bigger than all these other x's that you can just get rid of those. So now it's essentially just x to the 4th over x to the 3rd. Okay. It is important to note you can do that when x is going to infinity because infinity to the 4th power is bigger than 5x to the 3rd if x is infinity, 2x squared if x is going to infinity, and negative 7x. The infinity to the 4th power is way bigger, so we can just ignore all the other ones. This ends up just being x. Well, x is going to infinity, so that means this x is going to infinity. So your answer for this one is going to be positive infinity again. And that last one, we're going to do the exact same thing. We're going to infinity, so these are all meaningless here. So now you're going to have x to the 3rd over x to the 4th. So it's basically the last problem we did, only in reverse, which is equal to 1 over x. Well, x is going to infinity. So now you have 1 pizza divided by infinitely many people. That would just be basically 0. So again, your answer is 0 for that. So that's basically all of section 121. Let me know if you have any questions on any of these problems. All right. The last section of this first unit is all about continuity, and continuity is, it's very informally defined as, if you were drawing a function on an XY coordinate plane and you didn't have to lift your writing utensil up while you were writing that, and it's still a function, then you could say that the function is continuous at all of those points. We're actually going to formalize that definition of continuity a little bit in this video here in this section. So that's why it's in the limit section. You're going to need limits to basically define continuity. All right, real quick, let's do a discontinuity review. It says, what are the discontinuities of some common functions? Okay, polynomials. It is important to note that polynomials are continuous everywhere. Okay, so I'm going to write what are the discontinuities? There are none. Okay, polynomials are always continuous, so you don't need to worry about that. Exponential functions, same thing. You're not dividing by 0 on either the polynomial or the exponential, so there are no discontinuities. They're continuous everywhere. Trigonometric functions, on the other hand, anytime you divide by 0, there is going to be a discontinuity. Okay, if it's a 0 over 0, it's going to be a whole. It's still discontinuous. If it's a non-zero over 0, then it's a vertical asymptote. Either way, it's going to be non-continuous because there's a division by 0. If you had something like, I don't know, y equals, sine x or y equals cosine x, those are continuous everywhere. But if you have something like y equals tan x, so I'm going to write that down, continuous from negative infinity to infinity. But tan x, on the other hand, is not continuous because tan x is actually sine of x divided by cosine of x, and cosine of x can be equal to 0. So since tan is a ratio, you're dividing by that cosine of x. That means that you could technically be dividing by 0. So trigonometric functions do have instances where you are dividing by 0. Root functions, you cannot take the square root of a negative. So, okay, so it'd be not continuous there if you did a square root, or really any even root. You can't do the negative of that. So anytime there's a square root of a negative, that's going to be a problem. Rational, same thing as the trigonometric. You could be divided by 0 with rational. If you think about a rational expression like x squared over x minus 3, we'll just make this an equation. X equals 3, it's going to be non-continuous, discontinuous, because you'd be divided by 0 there. So this is important considerations for continuity, kind of things I already said. Can't divide by 0, and you can't take the square root of a negative because there's no imaginary numbers in calculus. Let's look at some problems here. This first one, we got a bunch of examples of continuity with graphs. So this first one, it's continuous on the interval. You can see it's continuous from A to B. There's no holes, jumps, or gaps. This one, on the other hand, isn't because there's a hole right there. Even though there's another spot right here at C, it's still, you would have to lift your pencil up off the paper to draw this. So it's not continuous on the interval. C, there's a jump, not continuous. And here, D, there's an asymptote, so that's not continuous. So I have the version that is continuous, that first one, graph A, and then all the other ones are examples of not being continuous. The first thing I said, one of the first things I said when we started this section was that limits can be used to define continuity, and here is the limit definition of continuity. And basically what this is saying is the limit from the right, if it's equal to the limit from the left, and it's also equal right in the middle, that's what this is, f of c, then it's continuous at c. Okay, so if I drew an example of this, just to kind of show you what I mean. So let's just say this is C right here. Okay, did something like this. Okay, if you notice, the limit from one side is equal to the limit from the other, and then it's also defined exactly at C. Therefore, you would say that it's continuous at C. Now, if you broke any of those, so if you make it where one of those is not true, then it's just not continuous anymore. So for example, if I drew something, if I drew a graph like this instead. Okay, the limit does not agree on both sides. You can see this one's up here and this one's down here. The limit does not agree on both sides. You can also just see from the graph that it's not continuous. Okay, if I did something where the limit does actually exist there, so let's just make this a whole now and do some function like that, you'll notice it's not continuous because even though the limits agree on both sides, it's not actually defined at f of c. So f of c is undefined here, which is that last part that has to be true for the limit definition of continuity right here. That has to be true, and it's not for this example. Okay, it's not equal to the limit of both sides, so therefore it's not continuous. So you make sure you understand the limit definition of continuity. If you are solving any problems and it says, prove the continuity at this point, my best advice that I can give you to solve those problems is start here. Start by writing down the limit definition of continuity and then filling in each of those. And you're going to see that while we do a couple of example problems toward the end of this section. Okay, but make sure you burn this into your memory because you are definitely going to need this to solve continuity problems. Okay, there's different flavors of continuity. Okay, we have removable discontinuity. I always like to think of it as a hole here, and you just remove that hole, or fill in the hole, I guess. Then it's magically continuous now because the hole's not there anymore. So that's kind of how I always remember removable. Jump continuity, it actually looks like there's like a jump from one step to the other. And then infinite discontinuity, you should know from the last section that asymptotes go to positive infinity or negative infinity. So it has the word infinity in it, infinite discontinuity. It kind of helps with understanding the types of those. So make sure you understand those three types. Here is an example right here that kind of highlights this. Right here, the limit doesn't exist. The limit doesn't exist at -2 because there's a jump discontinuity here. So that's an example. There's infinite discontinuity right here because of that asymptote. Here, there's a removable discontinuity because if I just got rid of this hole, now it's magically continuous. This one right here, it looks like there's a jump, so that's a jump discontinuity. So it's just kind of showing you all those discontinuities in action all in the same function. Okay, removable discontinuity, we already talked about that. This is where it occurs at holes. But if you want to look at it in terms of limits, you can kind of see, as long as it's not equal to it at that point, but the limits from both sides do agree. Okay, if the limits from both sides do agree, then that's removable discontinuity because it's a hole occurring. Kind of already just showed you an example. So if you want to rewind this video, you can kind of see that again. Or I can just draw it real quick right here. So say I had something where the limit does agree on both sides here. So on this side, it agrees with where it's approaching. It's not equal to it at that spot, though. That would be the f of c. And if you notice it's a hole, it's not defined. So this part is why it says not equal to. Okay, the other parts are equal. Non-removable, on the other hand, that's when the limit on one side does not equal the limit on the other. It doesn't even matter what f of c is. Okay, so that's a jump discontinuity or a vertical asymptote or an infinite discontinuity there. Here is what I basically just said all broken down. So discontinuities can be broken into two main categories, removable and non-removable. Non-removable is just that jump discontinuity and infinite discontinuity. Removable involves holes, non-removable jumps, gaps, vertical asymptotes. Make sure you understand that. Next thing here is intermediate value theorem. Intermediate value theorem is a very, very basic theorem that basically just states if you have a continuous function, okay, if you have a continuous function, I'm just going to draw a continuous function like this here. If there's a value here and there's a value here, so let's just say this is at A and this is at B, there is some value in between. Okay, intermediate means in between, so I always like to think about it as in between value theorem. It just means there's an in between value between A and B. That only happens if it's continuous. So if there's a function that's continuous, there has to be a value in between because there's no holes, jumps, or gaps. That value exists. So that's intermediate value theorem. If it's continuous, there's a value in between. Make sure you burn that in your brain. All right, let's go over this first example problem right here. The graph of a function f is shown below. What are the values of x that has a removable discontinuity? If you remember, removable is just a hole, but the limit agrees on both sides. That's what's happening right here. So the answer would be 2 for this one and 0. Okay. This one, although it's a hole, it doesn't agree on both sides, so it can't be at 1. So the answer should just be C, 0 and 2 only. The next one, we have a piecewise function, and it just says which of the following statements is false. Okay, if something is continuous, that means it has to be equal at that spot, as well as the limits have to agree on both spots. So if you look at it, is it continuous at 1? Well, let's just take the one that's less than 1 right here. So if you plug 1 in there, you get 3. Equal to 1, it's equal to 3. And then if you plug in 1 to this one right here, because it says x is greater than 1, you also get 3. So which of them is false? Well, this one's true. It is continuous at 1, so it's not that one. Okay, 2. At 2, we're going to be using this piece right here, and if you plug 2 into this, that is definitely continuous because it's a polynomial. I'm going to write that down. That's a polynomial at x equals 2. Because it's that x to the third plus x squared plus x. So it is continuous because all polynomials are continuous. And 2 is between 1 and 3, so that's why we know to use that piece. So either way, it's continuous, and we're looking for the one that's false. Okay, 3, okay, if you plug 3 into this, you get 27 plus 9 is 36, plus another 3 is 39. So one side you're going to get 39. The other one you get 0. So right away we know that that's not continuous, so C is the answer. But for fun, let's just check 4. 4 is when x is greater than 3, so we're going to use that piece. This is a polynomial as well, so it's continuous, so it's not D. The answer should be C for that one. Same kind of thing is occurring for example problem number 3. It says, let the function given f be the function given above. Which of the following intervals is continuous? All right, so we're looking for where it's continuous. Okay, this one actually covers 2 pieces right here. So that means there's that overlap of 0, which is in between these two right here. And since it's different pieces and they're not equal to each other at 0, it cannot be a, because that means there's going to be a jump. The next one, pi over 4 to pi, that one actually is all in the same piece of cosine, and cosine is continuous, so b ends up being the answer for that one. But let's keep going through the other ones to see why it's not those as well. Pi to 7 pi over 4, that would be this piece into this piece here. Since it's two different pieces, that means there's a jump. It's not going to be equal in that one on both sides. And then 7 pi over 4, and then same thing with this one. There's two pieces, so it's not going to be that one. So B is the answer for this one. Again, when in doubt, graph it out, graph all those pieces out, and you can kind of see that there's a jump. Actually, I'm going to show you what that looks like really quick. Here's that second one we did. You can kind of actually see why this one would not be continuous because there's that jump there. Okay, and the jump is at 3. So that was number 2. Number 3, though, this one, crazy looking function here. Let me default zoom, blow this up a little bit. You can kind of see exactly what's going on in each of the intervals. You can see at 0, there's a jump. At whatever this value is right here, 3 pi over 2, there's a jump. And then at 2 pi, there's an asymptote there. So that kind of helps drawing a picture of it. But you also should be able to know how to do it without a calculator as well. Let's go on to the next one here, example problem number 4. Okay, this one, it says let f be a function defined above. You're trying to find a value of b such that this is continuous. This is where you actually want to start with the limit definition of continuity. So we're going to say the limit as x approaches, in this case 2, of f of x. We're going to put a little plus sign there. So from the right has to be equal to the limit as x approaches 2 from the left of f of x. And it has to be equal to whatever f of 2 actually is. Okay, first thing I'm going to do, if it's 2 on the right, it has to be greater than it. So we're going to use this piece right here. And I'm going to plug in 2 for all those x's. So now it's 2b plus 2b. We're going to plug in 2 for this other piece here, because now it's the left side of it has to be less than 2. So now it's going to be 4 plus b squared. And then the equal one is actually the same thing as this one right here. So it's just going to be 2b plus 2b. So we don't really need to write it over again, but I'm just going to do it for fun. But it's already written in the red, so it doesn't really matter. I'm going to simplify this to be 4b is equal to 4 plus b squared. And then I'm just going to solve that quadratic. I'm going to subtract 4b from both sides, minus 4b plus 4. Okay, this one does factor nicely, so you can solve for b. It's just going to be 0 is equal to b minus 2 quantity squared, which means the answer is going to be b is equal to 2. So if b was equal to 2, that would be continuous. This function right here would be continuous between these two pieces. Any other value, it would not actually work out. And that's a lot to take in, so I'm actually going to show you on a graph what this looks like. Here's that fourth function here, graphed. And here's where b is actually equal to 2. But what I want you to see is that if I change this value to something else, it's going to make it where it's not continuous. You see how there's a jump there? Because I changed this value of b. If I go the other way, there's going to be a jump. It only works at 2. This looks close, but if you actually zoomed in, you'd see that it is still a jump. Whoops. You'd still see that it's a jump. So the main moral of the story is b has to be equal to 2 in order for that to work. And then you can see, even if you zoom in, it's exactly equal to it right over it. Okay, onward we go. Problem number 5. All right, select all correct answers based on the graph below here. Okay, so the limit exists on both sides. Okay, it definitely exists going this way. It definitely exists going this way, so that's definitely correct. The next one, it says the limit as you approach 2 exists. That one does not, because this one does not equal that one. So because they're not equal, the limit does not exist at x equals 2. F of 2 is defined because you can see it right there. It's defined right there as -4. Okay. F is continuous at x equals 2. Definitely not. There's clearly a jump here, so that doesn't work. And then none of the above doesn't work either. So the answer for this one should be A and C. Okay, this is similar to the problem we did before where we had to find B, only this time we're finding K. So to solve this one, we are going to use the limit definition of continuity. So the limit as x approaches, in this case, -3 of g of x from one side has to be equal to the limit as you plug in -3 from the other side of g of x, and that should be equal to g of -3. Okay, one side and the other are actually both based off of the same piece, this one right here, because it says it's not equal to -3. Well, that means it could be greater than -3 or less than -3. So these are actually the same thing. I'm just going to lump them up together. So if you plug in -3 on this, you're going to get a 0 over 0. So what we need to do now, if I combine these here, what we need to do is factor that into something like this and solve this limit. So this is rehashing the old stuff that we were doing already before. Now you can do direct substitution on this and you get -1. Okay, well that needs to be equal to g of -3. Well, g of -3 is equal to k. So that means k is equal to -1. So the answer for this one is just going to be -1. Let's look at a graph version of this, just to kind of get an understanding of what's going on here. So the graph's going to look like this, and here's k. Right there, you can see that it's directly over it, but if I moved this, it would not be, because right there, there's actually a hole. So you have to basically filling that hole. And to fill that hole, you would have to move this up, and it's going to be -1. Oops. -1, and then you'll notice that it's right over it, and it fills that hole. Okay, last one that we're going to do, it says between which of these two values does this equal to 0? Okay, the easiest way to do this is to plug in all of those values, those x values, a, b, c, and d, to figure out, is one negative and one positive, and if that's so, then it actually can be equal to 0. So what I'm going to do is make a table. So we have x here, and then the other side of the table, we're going to have that 3x cubed plus 5x minus 1. Okay, and I'm going to plug in all of the values that are given in the multiple choice. So basically -2, -1, 0, 1, and 2. -2, -1, 0, 1, and 2. And I'm going to plug those in to that 3x cubed plus 5x minus 1. Okay, so if you do that, you should end up with -45, -19, -11, -3, and 23. So now we're looking for it. This is a polynomial, so it has to be continuous. This is a polynomial. So oh, I'm sorry, this is -11. It has to be continuous, so we're looking for, for it to be equal to 0, that means it has to go from positive to negative, which this one right here does. It goes from -3 to positive 23. That means 0 was in the middle. This is an intermediate value theorem problem, an in-between value theorem problem, basically. In between, there's a problem in between, or a value in between, so then the answer has to be D between 1 and 2. So that's basically the last section of the unit. If you have any questions about anything in this video, let me know.